So this is when we start getting into the weeds a little bit about how we actually look at the bits that make up the numbers inside of the computer. We talked in the last one about how the negative sign in the CPSR is set by the most significant bit of the number in the register or in the result if not we're not using a number in a register. And so we can use this to check if we have two numbers that have a sign that matches. And so let's just look at a byte for now. And if we have a number like 74 and we have a number like 4, you can see that the most significant bit is 0 in both of them. And if we have a number like negative 74 and negative 4, you can see the most significant bit is 1 in both of them. But if we have negative 74 and 74, it varies from one to the other. And so we don't actually care about any other bits if we're just trying to find out if we have two positive or two negative numbers. We're really just worried about the most significant bit of these numbers. And we can use this to our advantage. So let's start writing our code, and when we get to that point, I'll actually explain how this is going to work. The first thing that we need to do is actually load the list of numbers. And so let's start a register list. Put them in R4. Load register. After this, what we need to do is we need to have a place to count the number of groups, the number of times that we have two numbers that have matching signs. And so we'll put that in register 5, because it's the next one. And again, I'm going to initialize this even though you technically don't have to. And so now that we have this set up, we can actually work on the actual loop. And so for this, let's do the things we know that we have to do. The first thing that we have to do is we have to load the first number. And so we'll use load register. And then we're doing positive and negative, so we need the S. But this time, notice we're not using bytes, we're using short words or half words. And so we also need to include H instead of B. B would read a byte, but these are 2 bytes long. And so we need to use an H instead of a B. And let's do the first number in R6. And that'll be from the number list. And when we increment this, we're not going to use 1 because it only moved 1 byte. We're going to use 2, so it moves 2 bytes. It moves to the next number. And so up here, let's just make a note saying R6 is number 1. And R7 is number 2 to compare. And so we know that we're also going to have to load the second one. And again, increment 2 after. And so we need to test these. And if you look at the list of bit operations, you can see that there's one that may help us here. We have the exclusive OR. You'll see it written as EOR or XOR. But what it does is if both of the values are similar, then you'll have a 0. And if one of them is a 1 and the other one is a 0, then it'll be 1. And what we can do is we can test these values and look at the negative flag. Because if both of them are negative, then we have a 1 in the most significant in both of them, and it'll make the CPSR 0 for the negative. If we have positive, both of them will be 0, and the CPSR for negative will be 0. But if we have a negative and a positive, it'll make the most significant bit 1, which will make the negative flag in the CPSR 1. So now that we've loaded the two numbers, what we need to do is we need to compare them. And what we can do is, other than the comp instruction, there's other instructions that we can do, and most of them work on these bitwise operations. And so let's look specifically at the exclusive OR. You'll see this sometimes as XOR or EOR, and it's just the exclusive OR. But the way this works is that if we have two bits that are the same, then it'll produce a 0. But if we have two bits, one is a 1 and one is a 0, it'll produce a 1. So let's think about this. If our first number is positive, the most significant bit is going to be 0. If our second number is positive, then our most significant bit is going to be 0. And if we do an XOR of those two, it'll be 0. The same thing with negative. If we have two negative numbers, the most significant bit on both of those is going to be 1. If we XOR that, then it'll result in a 0. But if we have one positive number and one negative number, then we get a 1, because one of the most significant bits will be 1 and the other one will be 0. And so what we can do is we can use the instruction TEQ to XOR these two numbers, to exclusive OR these two numbers, and put the result into the CPSR. And this doesn't store the value anywhere. It just sets the flags on depending on what the result is. So we want to add 1 to the count if they're the same. So we know we want to add 1 to a count, which is in R5. But when? And so we can use our suffixes again. But as I said multiple exercises ago, the suffixes really only make sense if you're comparing it, and sometimes only when you're comparing it to 0. But if you look at the descriptions of it, there is a suffix that only operates on the negative flag, or I mean 2, and that's really all we care about. We don't care about all the other bits, we just care if that most significant bit is set. Because if the exclusive OR results in a bit that has the most significant bit as a 0, then we have the same number. If we have a result from the XOR that has a 1 in the most significant bit, then they're different. And that most significant bit is what sets the negative flag. And so what we want to do is we only want to add 1 if that negative flag is 0. And if you need to take a second to think about that, because this is the first time really that we're taking these numbers and not working on them as like numbers, but actually looking at the bits that make up the numbers. And so we're going to add 1 if the signs are similar. And then that's our loop. The other thing that we need to do is actually find an exit condition here. And so we'll put it right here. If this first number that we read is 0, then we need to get out of the loop. And then again, we'll just use exit. And so here we'll put our exit label. And now all the hard work is done. This will compare every two numbers, and if they have the same sign, it'll add 1 to our counter. If not, it will not add 1. So we're going to use our integer to ASCII module that we kind of set up. Again, the first parameter that we need to put to it is the number that we want to convert. And in this instance, it's the number of groups, so R5. And then our address space, we need to create some address space down here. Again, we need, Gil. We need 10 bytes for the numbers, and the line ending is 11, so 11 bytes. And this is actually going to be a load register. R1 outstring. And then we can invoke it using a branch and link like that. Now we have the ASCII code in our outstring address. We can set up our write. Move R7. 4 is our write supervisor call. First parameter is going to be 1 for standard out. Second parameter is going to be our outstring. And then our last parameter is going to be the length. We'll put R2 this time and not R3 again. And then invoke it using supervisor call 0. And then all we need to do after that is write, or exit the program. Oh, exit is 1, not 0. And then the only parameter that we need is the error code, and we'll put that in R0. And then supervisor call 0. And then that should be everything. So let's try compiling this and see what we get. And so what we're going to do is I'm going to run this by using our makefile, and then run the program, and we get 27, and that's what we should get.